Professor Philippe Jaming from the University of Bordeaux. Philippe Jaming obtained his PhD from the University of Orléans in 1998 under the supervision of Aline Bonamy. He was assistant professor in Orléans from 1999 to 2010. He was then hired as a full professor at the University of Bordeaux. His research topic focused on harmonic analysis and its applications, especially uncertainty principles and phase retrieval. And he recently got interested also in applications of to control theory. He published around 60 papers and notes and 10 conference proceedings. He has around 50 collaborators and he supervised 7 PhD dissertations. He's also involved in community service. Since he has been organizing more than 10 international conferences, he's editor of Analysis Mathematica and Journal of Fourier Analysis and its Applications. And he also led to 5 exchange programs on harmonic analysis with Austria, Hungary, Norway, and Tunisia. And I would also point that he's also the head of the Mathematics and Applications Master Program at the University of Bordeaux. Now I let Philippe starting his talk.
Okay, so thank you very much for the introduction. So my talk will be about literal problem for non-harmonic trigonometric polynomials, and my first task will be to explain the words in the title. This is joint work with my colleague Karim Kelly and also our joint student Shadi Saba, and a little piece of what I will tell about is also with another student, Yunlei Wang. Okay, everything is already in some papers that are available. There's also a survey that I wrote after last year's last year's conference of the Tunisian Math Society. So there's a lot of sources for what I will speak about today. So what are we talking about? So trigonometric polynomials, those that are called harmonic, it's another word for periodic. In this case, they're just what you know as trigonometric polynomials. And for me, there will always be one periodic. It's a little bit more convenient. So there are linear combinations of exponentials, e to the 2i pi n j t. And when the nj's are integrals, we say that they're harmonic. So it's mainly because they are solutions of delta u equals 0, well, second derivative because one variable, u equals 0, but with boundary conditions that are periodic on the boundary of the 0-1 interval. And those that are non-harmonic, they're almost the same, except that the nj's are replaced by lambda j's that are real. So there's still some of CJE to the 2i pi lambda JT. But if the lambda j's are real, these are no longer periodic, so you lose this boundary condition. That is why they're called non-harmonic. So they're harmonic on the real line, but not on an interval with any boundary condition. Also, I will always suppose in this case that the lambda j's are separated. So I order them increasingly, and the gap between two consecutive ones is at least 1. And I will refer to these nj's and lambda j's often as frequencies. So the question we are asking is an old question. It's to give lower bounds, occasionally also upper bounds, of norms of this trigonometric polynomials in terms of norms of the coefficients. So in terms of signal processing is to see if the signal controls its components. That's the way you can look at it. And the choice of the norm will depend. What we want is something that depends on the set of frequencies. That's also called the spectrum, but with bounds that do not depend on n. So for instance, if I take the nj, say, to be the squares, I want general norm, lower bound of the norm of phi in terms of norms of CJs, but with a constant that is independent of n. Otherwise, it's just what we learn in second year. There exists always a constant by equivalence of norms in finite dimensions. So that is the first important feature here, is that the constants must not depend on this n, which is the number of terms I have. Okay, so just in case you have never drawn such pictures, which is well, I have not drawn them until very recently. What I draw here are examples of trigonometric polynomials. Okay, it's a bit drawn with colors to make them look nicer. But these objects are very simple trigonometric polynomials when you look at them as curves in the plane, not as one usually does as a function of time, where you represent real and imaginary powers. So you look at them as curves in the plane. The ones that are here are trigonometric polynomials, and just to tell you, they have been drawn by this object, which is called a spirograph. So if you have been a kid in the 70s or 80s, you surely had one, or one of your friends had one, because that is what we used when we got bored in class. We are drawing pictures with this. So the device is very simple. You see that you have gear wheels. See, they are dented. And you make them move in another one, and basically you put your pen in this thing and you just make it move, and it would make some sort of curve. So it's basically the sum of two exponentials that you're drawing. So now the question is, what happens for non-harmonic ones? Well, you see that the one in the middle, there are no dents. So if you do it with this one, your wheel, the little wheel in the middle, would slightly, even if you do it very well, would slightly glide, so that, whereas here the movement is periodic, here you would lose this periodicity. And the kind of curves that you would get are something like this. Okay, so these are non-harmonic ones. They're a bit more complicated than what you could draw with the other device. They have they are very simple. They're just 3 frequencies. Okay, nevertheless, you get this, yeah, the difference from one to the other is that I just added a small frequency, and you see this relatively different. So these objects are no longer periodic. They are almost periodic in the sense that if I take any point here and I wait long enough, I would go back near to it, well, roughly at some frequency. Okay, so now the question I'm asking is, looking at this curve, is there any way I can control the coefficients, at least as globally with some norm? Okay, so what are the norms we're speaking about? The norms we're speaking about here will be mainly L1 norms. So L1 norms are interesting because that's why I draw the curves. They represent more or less the length of the curve. To have the length of the curve, I would need to add a lambda j here. But this lambda j is fixed, so it's not a major difference. Okay, so this is the L1 norm. I can also see it as a norm on the coefficient Cj, which I call norm of Cj with capital L1, just because it's the norm of the trigonometric polynomial associated to it. So again, the lambda j is the frequencies, is a fixed set of frequencies. Interesting question is also how to get the frequencies, but this is not what I will speak about. So in the harmonic case, one usually takes t equals 1, but because here I take a mean and not just the integral, I could take t any integer in this case, or even let t go to infinity. Okay, In the non-harmonic case, there's another thing that is important to notice is that, well, when you teach Fourier series, you usually take symmetric sums. But for the question here, that it may not be very important, or it may be, but not on the size of this L1 norm, because I can just shift everything. Okay, and I can also add something fixed here. It will not change the L1 norm. So I can translate the set of frequencies. That will be important because in the sequel, I will usually translate it so as not to start at 0, but a little bit further. That is not very important. On the other hand, the coefficients here, notice that if I translate, I also translate the coefficients. So for most norms on the coefficients, they are made so that this is harmless. But if you use weighted norms, then this minus n enters the weight. And as I told you, I want estimates that do not depend on this minus n, so on this capital N. Okay, there's then another norm, which are these Bezikovich norms. They are the limit of L1 norms, of this mean L1 norms. This limit exists. That's why I take always finite sums. In the end, I can always use limiting arguments. That's a minor issue. And as I said, in the harmonic case, the Bezikovich norm is just a usual L1 norm. That will be convenient. Okay, on the coefficient side, I have the infinity norm, the L2 norm, and here I use either the analyst L2 norm or the probabilist L2 norm, and there's a factor of square root of n between them. So the probabilist L2 norm is the mean of the square that I then put to the power 1/2. Okay. I could use an L1 norm. So these three norms, you see that if I shift the sequence Cj, I will not change the norm. Okay. Also, what I didn't say is that if I have less than n coefficients, I just add zeros at the end. That's not a major issue. Okay, so if I'm in a C capital N plus 1, I'm also in C with something bigger. That's not a problem. Just add zeros at the end. Okay, and will not change the norm. Or if I cut the sequence, I will have a lower norm that will be used at some stage. So for the weighted L1 norms, here, if you see that if I put Cj minus n, I change the norm because I would have to put a plus n here, so I get a coefficient. So here I cannot shift harmlessly if I want to compare to this norm. That means that if I have symmetric sums, it's not the same thing as non-symmetric sums. Okay, so for the moment, I spoke about L1 norms, but I want to get rid of the L2 case first, because that is now very well known. Well, to start with, in the harmonic case, then it's just Parseval's identity. And when you take t equals 1, and if you take a t larger than 1, then it's not a big issue. You just go to the next multiple of 1, to the next integer, and you compare it. In the non-harmonic case, the Bezikovich L2 norm is the right one, because let me just go back 2 slides. If I take this, the Bezikovich has a L2 norm is squared, has a square here. And if you just take, you can associate this to a scalar product. And for this scalar product, all exponentials e to the 2i pi lambda t and e to the 2i pi mu t are orthogonal. So again, it's just Parseval. What is interesting is what you get when you fix t. And in this case, it has been proven by Ingham in the 1931, to be precise. Okay, here there's a condition, lambda j minus lambda k is bigger than 1, which is the same as lambda j minus lambda j plus 1 bigger than 1, if you order them. In this case, the L2 norm is comparable to the L2 norm of the coefficients with a lower and upper bound. Well, obviously you cannot take t less than 1 because already for Fourier series, something like this could be true. You can have a Fourier series that is 0 on an interval without the coefficients being 0, just because it's an orthonormal basis. So you take a function supported outside the interval, and you take its Fourier transform, and then letting n go to infinity, this thing would go to 0, whereas this, of course, not. Okay, so t has to be bigger than 1. If you take here, instead of 1, say gamma, the separation is gamma, then t has to be bigger than 1 over gamma by a straightforward scaling argument. But what Ingham also showed is that there exists at least one sequence, lambda j, for which such an inequality cannot hold for all n when you take t equals 1. And the sequence has just one gap. So for integers, you can take t equals 1, but the sequence that Ingham takes has just one gap that is not 1. Also know that here you could start the sums at minus n. It wouldn't change anything. Okay, the upper bound here is always true. It's the lower bound that fails. Okay, and what has been shown by Kahan first in the 60s is that if you have these gaps that go to infinity, then you can take t arbitrarily small. But that's a duality argument, so it doesn't give any information on the constants, a and b. To have an information on a constant that has been done later on in the early 90s by Haro in link with control theory. It's an inductive procedure on how to compute this A and B. Also, I didn't mention it so far, but Ingham's theorem, the A and the B are explicit constants. They are not, it's not just an existence. They can be computed. The optimal constants are not known, but they are explicit. Okay, let me just give a proof of Ingham because it's relatively simple, and it goes through the construction of an auxiliary function. So what you need is to find a function g that is supported in -1, 1, and has its maximum at 0. Okay, it could be, okay. I'm not saying anything about the sign, it's just that it's larger at 0 than anywhere else. And the Fourier transform, it would be nice if it could be supported in -1, 1, but that is, of course, impossible. Function and its Fourier transform cannot both be compactly supported because they would both be holomorphic and compactly supported, so 0. So what you ask is instead that it be a negative function outside -1, 1. Okay, it's also a real function so that everybody here is real. Yeah. And again, you want this function to be less than some constant on -1, 1. Okay, so what do we do? We do the following computation. The first one is you look at this integral, this L2 norm. I put the CG here because it's more convenient. So the CG, I put it inside, I get the G hat because G hat is less than CG on my interval -1, 1. So here I'm proving it for t equals 2. For t less than 2, you need to be a little bit more careful. Okay, so then you get this identity. The quantity you want to estimate is lower bounded by the integral of g hat of t times this mod squared. But g hat is negative outside -1, 1, so I can push this integral to r. I just add negative values, so I get something smaller. I subtract something from that. The next step consists of writing this double sum, this mod squared as a double sum. So it's sum of aj, ak bar, integral over r, g hat of t e to the 2I pi. So once I have lambda jt, and then I have its conjugate minus lambda k. And now I recognize here the Fourier inversion formula. forgot to say that G and G hat are in L1, so that I can apply the Fourier inversion formula. And this thing is then sum of AJ, AK bar, G of lambda J minus lambda K. And now I use my last property. The support of G is minus 1, 1, included in minus 1, 1. But lambda J minus lambda K, this is bigger than 1. So the only time this cannot be 0 is when lambda J minus lambda K is strictly less than 1. That can only happen when lambda J equals lambda K. So this double sum is actually a single sum. K has to be equal to J. I get this. So if I put this CG here, I have exactly my inequality on the right-hand side. Provided I find the G, and this G is given by this formula, you just take the cos pi t on minus 1/2, 1/2, and you self-convolve it, and you do the same with its derivative. So it's a weak H1 derivative, it's weak derivative. But on the Fourier side, you will get 4 pi squared 1 minus psi squared, so that times h hat squared. So you get this property for free with this. With any h, you get this for this property for free by taking this object here. Okay, and then the only thing that you need is to have a reasonable constant, is to compute this CG, and this check that this property is true as well. Okay, so that's the proof of Ingham, at least for t bigger than 2. I will not give the details. I will rather explain one example of how you can use this. And we use this for the control of the free Schrödinger equation. So the free Schrödinger equation here in the periodic one, okay, sorry, the period became 2 pi. You take the Schrödinger equation, the derivative with respect to t is minus I, the Laplacian. There's no potential here. Okay, you put periodic conditions, both for the function and its derivative, and initial value, you assume it's in L2. And then what you do is you can teach that in the first Fourier series classes. You can solve this equation with Fourier analysis. And what it tells is that if you know u entirely at time t, then you know u naught, because it's just inverting the Fourier series. What is more difficult is if you want to have u naught only on a smaller piece than on all intervals. You assume you cannot measure u entirely in space. So there was a result by Jafar that told you that all you needed is an open set in space-time. And what we did here is that actually you need only one sensor, but you make that move along a curve. So what you have here is, you know, u on a segment. So t is arbitrarily small. You know u on a segment that starts at the point t1, x1, and that moves at speed here. Minus a is just for convenience, could be plus a. Okay, well, this quantity is always controlled by the sum of the ck's are the Fourier coefficients of u naught, so that is by the L2 norm of u naught. And what we proved is that also is, that's not very difficult, that's the upper bound in Ingham. It also goes the other way, provided the speed is not an integer. And let me just quickly sketch it. The beginning is what I already said, is you solve Schrödinger equation via Fourier series, and you just plug this into it, and you get this. This series is L2 convergence. There's absolutely no difficulty there. The T1, X1 is really harmless. You put it in the decay, it will get into the CK. You group it with this, just by e to the I k squared T1, you add it to the CK, you get something that has same modulus, so it's not important. And what is really left is this I k squared minus AK. So this is your set of frequencies, the k squared minus AK. So I write this as a sum of lambda. This should be a capital lambda. Sorry, again, forgot to to correct that. D lambda E to the I lambda T, where lambda is the set of frequencies, the K squared minus AK. And now there's this very little simple trick which is basically completing the square. If you take two different frequencies, K squared minus AK and M squared minus AM, then you can factor it out as K minus M times K plus M minus A. This, if K is not equal to M, is always at least 1. And this piece here, if A is not an integer, it's at least the distance of A to the integer. So this cannot vanish. So they are really all different frequencies. And moreover, if you let K go to infinity and you take M equals K minus 1, then this thing goes to infinity. So this is a sequence of frequencies that if you reorder them properly, it's a thing that has gaps going to infinity. So you can apply just apply Ingham. Okay, and now our question was, can you, instead of measuring this energy, can you have something when you just follow the curve and measure the solution here? This is the solution, and assume you can see where it is in the complex plane and you follow it, but you can just measure the length. Do you still have something like this? And I will show you that yes, by just the same trick that is here. Okay, there's another trick that comes from number theory. There's also a link with of L1 norms of trigonometric series with number theory. But this goes to the L4 norm, and there's the L4 norm of, so here is only an exponential sums. It's a trigonometric series with 0, 1 coefficients. And then there's a very simple thing that says that the L4 norm to the power 4 is the so-called additive energy, and it's the number of solution of the equation nj plus nk equals nj prime plus nk prime, where the set of nj's are the frequencies that appear. Let me show you why this is true. It's just Parseval. You write the L4 norm to the power 4 as the L2 norm to the power 2 of the square. It's looks kind of stupid, but that's what you're doing. Now you write, what is the L2 norm? It's the integral of the function, so the square of this exponential sum, times its conjugate. So the square of this exponential sum, you see here I have a minus because that's the conjugate. Okay, now what I do is that I expand this square sum is a double sum, and a product of double sums is a quadruple sum. What do I have? I will have an nj, an nk from here, minus an nj prime, minus nk prime that come from here. So I'm left with this quadruple sum. These are finite sums, so I have no problem exchanging summation and integrals. And when I put the integral in here, what do you have? I have an integral of an exponential that is 0 if the frequency in there is not 0 and 1 otherwise. So I just count the number of times this thing here is 0. That's exactly what I said. And then I leave it as an exercise for you that because of Parseval, in this case, the L2 norm squared is n. If I use the right holder between L1, L2, and L4, I get that the L1 norm is lower bounded by n to the cubed over the additive energy, the whole thing to the power 1/2. Okay, this tells us something. If this set is sort of random, then then there are little chances that you have many relations in it. On the other hand, if the set is very structured, then you would have many relations. So the L1 norm should be small. And if you have something in between, there must not be too many relations. That's the idea that you're having here. And this will lead me to what is the Littlewood conjecture. So I will soon arrive to it. But let me just illustrate this a little bit more. If the nj's are an arithmetic sequence, just whether it's an arithmetic sequence or just the sequence nj equals j is the same thing. The L1 norm is just the L1. What you have here is just the Dirichlet kernel. And the L1 norm of the Dirichlet kernel, I think everybody that has had a course on Dirichlet, on Fourier series knows that it grows like log n, because that's why Fourier series can diverge. That the Dirichlet kernel is not an approximation of unity. And if you work a bit more, you can see that the constant is 4 over pi squared. It's actually log n is exactly the order and it's 4 over pi squared, and the next term is a little off capital N. Oh, it goes to 0. It's a little off 1. There's a little recent result, so maybe that is not easy to explain online. NJ is what we call a double arithmetic sequence. So you see that you do small steps of size d, and you add this to big steps. So you make a big step of 100, and around of it you put small steps of 1. And then from this big step of 100, you start again, you go again 100, and then you put small steps of size 1. And the small steps you have capital N, and the big steps you have capital N. And in this case, the growth is like log m log n. So there are some conditions on n and m for this to be true, but basically they just need to be large enough. And there's some relation between the steps, but okay. There's this more famous result by Zygmunt that for lacunary sequences, the L1 norm, so if the frequencies are lacunary, so typically just think of a geometric sequence. Then the L1 norm is equivalent to the L2 norm of the coefficients. Okay, in particular, if all the coefficients are 1, I get very far from log n of the arithmetic sequence, I get square root of n. Okay, it turns out that the same is true for the non-harmonic case. Probably also for, when you take the basic OH norm, probably also if you take L1. So, I didn't really check that. Okay, let me take another example, the set of squares. Well, here something strange happens. So it was known on the 30th, I don't remember the date, that if you just take the exponential sum, so all the CJs are 1, then the L1 norm grows again like square root of n. So just for future use, note that I can write this as square root of n times the expectation of the CJs. Okay. If I just take a small variation, L1 variation, I still have the same bound. That is just because the error I do is bounded by a constant. So that's not much. And what we managed to prove, it's basically an adaptation of the Dijkstra's proof, is that the correction term in general is the L2 norm over the L1 norm. So that's the L1 norm of the increment of the sequence. So a sequence, you can see it as the successive values, or also as the initial value and then the increments. How much you need to move to go from term j to terms, what, j minus 1 should say, to terms j. So you take the L1 norm of the increments, and that's what you find here. So in particular, we also get square root of n when you have an increasing sequence between two values. Okay. Okay, all this kind of examples, those that were already here when Littlewood were still alive, led him to, I would say, speculate that if you take an L1 norm of a trigonometric polynomial, the smallest value is attained for an arithmetic progression. Okay, this is, I don't know if Littlewood really said it, to be honest. It's called the strong Littlewood conjecture. You have to read between the lines to think that Littlewood said something like this. What he really said is that this quantity, the smallest possible L1 norm of an exponential sum, grows at least like log n. And the constant has to be less than 4 pi squared, because this is what you can do with the Dirichlet series. Okay, and it turns out that this this version of the Littlewood conjecture has been proved by Konyagin, McGee, and Pinho-Smith in 2 independent papers, but the same year, 81. Both of them actually prove something stronger. And let me state what little bit of history. There has been a long series of work, but the first non-trivial result is due by Cohen, and you see that we're still very far from log n, because it has a power 1/8, and then there was some progress. It managed to go to log n over log n squared. So this is a number series like this, and we like to make jokes about them, like you know what a drowning number series says. I'm in an applied math, so I can say nasty jokes about number series. Well, when a number series drowns, he says log, 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 log. Okay, so that's a bit of drowning, logs. Okay, but the big thing is that was a major result in harmonic analysis in the very early 80s, is that actually it's log n. It's even stronger because it's valid for all trigonometric polynomials. And what you have on the right is this weighted L1 norm. Okay, so if you take all the Cj's equals to 1, you get sum of 1 over j plus 1 from 0 to n, and that is like log n, as you all know. Moreover, the constant that is here is, it's not just there exists some constant that is arbitrarily small. It wasn't too bad. It was 1 over 30. And then the year after, there has been a slight improvement in the case, again, misprint. All the Cj's are larger than 1. In this case, you can improve the constant, the proof by these people has been done by 2 people. Well, actually, the difficult to read is they explain how to modify the proof to get a constant that is actually not equal to 4 pi cubed. This is not what they find. They find some constant that up to 5 digits is the same as 4 pi cubed. So it's easier to compare with the strong conjecture, which is 4 pi squared. Okay, so we are off by a factor slightly larger than 3. That's still the best. This one is still the best that one can do. This one, I will show you a slight improvement. There was also an a version actually by Ingham, and because of Maggie Pinho-Smith, this has been a bit forgotten, but Ingham proved that there's a lower bound with the L infinity norm. And a very reasonable constant. And also this one is true up to t equals 1, and it's true for all real frequencies. So in some sense, it's a much stronger result. It's also a much stronger result because here you see, because this you can shift, this you can write symmetric sums, whereas here you cannot write a thing like sum from j equals minus n to n, and here sum from minus n to n absolute value of j plus 1, which would be a natural conjecture. And this is actually false, because if you take nj equals j, you could just put here the Feyer kernel. You would have 1 on this side and still log n of n. So this is really a one-sided version. The two-sided is just not true in full generality. It could still be true for some sequence of integers. This we don't know. But it's true at least if you take a lacunary sequence. Okay, what happens in the real case? Well, in the real case, there was a result by Hudson and Legband that showed that at least for the Bezikovich norm, you get exactly the same result, and the constant is the same. It's not just it happens to be the same. It is really the same because it's a result that transfers. You can transfer the result from integer frequencies to Bezikovich norms for real frequencies. And a few years after, Nazarov proved that the same is true for L1 norms. So this time t is fixed. Here there's a limit, provided this t is bigger than 1. Okay, so there are 2 things. The result by Nazarov is very nice, but difficult to read, I think, but nice. but there are two drawbacks that we wanted to settle. The first one is that this CT is not explicit. It doesn't get any estimate of the constant. We'll explain that a bit later. The other thing is, and this is still the case, t equals 1 is open. Is this true or not? If you look at Ingham L2, you would say that it is not. And if you look at Ingham L1 result, you would say that it may be possible. But I have no idea right now. You cannot get that from Nazarov's proof. This I'm sure. Okay, just a word on Hudson and Legband. The idea is very simple. It's using the Dirichlet simultaneous approximation property. You approximate each, because you have only a finite number of them, you approximate each real frequency by rationals with same numerator. That's the Dirichlet simultaneous approximation. So the exponentials are also approximated. And then you take the MK periodic trigonometric polynomial that you get with these rational frequencies, and you get this estimate between the difference. Okay, if you use McGee-Pignot-Smith, but not for one periodic functions, for MK periodic, you get exactly this. And then you plug it in -phi plus phi, and you get this. And what you see, this piece here, the one that depends on the approximation, doesn't depend on the K. So now you let K go to infinity, that is MK go to infinity. This goes to the Bezikovich norm. And then you can let epsilon go to 0. So this term goes. And that's just the proof. So you see, it's very strong, it's very flexible. Basically, if you have a reasonable condition on the lambda j's, you would have a similar condition on the nj case here. And so you can transfer results from the periodic to the non-periodic case. Okay. So it's time to give my own results. So what did we prove? We actually made Nazarov quantitative. And what we're having is the following. For the Bezikovich norm, we get 1/26. So that actually improves McGee-Pignot-Smith, because when the lambda j's are integer, they had 1/30, so slightly better. Unfortunately, for the Littlewood conjecture, we have no improvement, because the best result was 4 pi cubed, and we still have 4 pi cubed. So the strange thing is that both results, Yabuta, Stegeman, and ours, we get this. It's actually not 4 pi cubed, it's some number that is a solution of an equation. And you do it numerically, you look for this equation numerically, and you find something with 5 digits, which is the same as this. And it turns out we get the same digits in all 3 papers, but much more than 5. It's like 12 digits that are the same. So it's not the same equation. So it's possible it's the same thing, and that is the real value. For the moment, I have no clue for this. Okay, so this is for t going to infinity. It turns out that our proof also works for t fixed. So the main thing, Nazarov uses an auxiliary function that we have strongly modified. And we also added several parameters that basically the ideas that are hidden in Yabuta and Stegeman's proof that are implemented. And in this case, we can get a very reasonable quantitative estimate. Basically, it's reasonable starting from t equals 72, which is not too bad. The constant is 1/122. It degenerates very strongly when we get t smaller. I don't remember exactly, but for t equals 20, we had something like 1/billions, so it becomes useless. Okay. And then after this, we looked at Nazarov's proof, and with a slight modification, we get that this constant, so the constant is on the right-hand side. So when t goes to 1, you stop having anything because you have something going to 0, and the speed at which it goes to 0 is t minus 1 to the 7/2. With a little bit more work, you get anything strictly larger than 3. So it's not very inviting to think that t equals 1 is true, but on the other hand, it's not sure that it's even a power. So it's just what the proof gives. That's the best you can get out of the proof. Okay, because you need a little bit of room. So you need to have a t strictly larger than 1 to make the proof work. So there's nothing you can do with that. Okay, and then comes the question whether the result by Kahan and Haro works. If the frequencies go to infinity, can you take this t arbitrary small? And that is where my other student, Yunlei Wang, comes into the game. And the fact it is actually true. So I told you that Kahan and Haro had this result for the L2 case, and they both use the upper bound as well as the lower bound. So this doesn't work here, and we needed a totally different proof. And okay, so my questions are this, and then I will sketch the proof quickly. So again, is this t bigger than 1 necessary? And the other question is there anything like a two-sided estimate? Say something like this. If you take the lambda j symmetric, you would expect this. I already said it cannot be true in full generality. And the condition we think is needed, well, there is one needed because of the failure kernel. We more or less would like to conjecture that is some of the 1 over lambda j's converges, but we have no real reason for that. Do I still have 5 minutes? Is it? Okay. So if I have 5 minutes, I would give you.
Yes, please.
Okay. I would like to give you a quick sketch of the proof of this fact, because the proof is non-quantitative. So we just know that there exists a constant such that this holds. And so this is why I think that this condition is also needed for the symmetric case. We have it here. Then you also get Ingham's version with t arbitrary small. The original results are t bigger than 1, and now we can, if the gaps go to infinity, we can take a t arbitrary small. That is really what we wanted, to have a reasonable analog of my controlled result with Vilmos-Komarnik, which was an L2 result. Now with this, exactly the same proof will give you an L1 result. Okay, so what do we do? Well, it's a matter of equivalence of norms, but with constants that are independent of n. So the two norms that we are considering is this L1 norm. So it's really a norm on the coefficients. Okay, if this is 0, then all the coefficients are 0. That's the only thing that needs to be done. And this weighted L1 norm. So if I fix n, all norms are equivalent. So this one I don't need. The one that I'm interested in is this one. So there exists a constant, but it depends on n. And my aim is to show that if my lambda k have gaps going to infinity, I can choose an a that is independent of n. Okay? But if the gaps go to infinity, well, after some stage, my gaps are bigger than 1 over t, the t that I took here. If t is bigger than 1, it's already proven, so I take a small t. So at some stage, my gaps will be bigger than 1 over t, and Nazarov's result tells me that I have a constant. But I have to throw away from k equals 0 to this nt, t minus 1. Okay, so I have this. So assume I cannot do this, mean not have an a independent of n. So what does it mean? It means that for every n, I can find a length and n, a vector that has a weighted norm 1, but this L1 norm 1 over n. So in this case, I cannot bound lower bound this by this, because this stays fixed, this goes to 0. Because of equivalence of norm, these vectors necessarily have lengths going to infinity. So there is no loss of generality by throwing terms away, that I take the length to be strictly increasing and always longer than this length given for which Nazarov's is true. And then I do the natural thing, is that I split this vector. So there's an abuse of notation. This one has the first nt coordinates, and this one has all the remaining ones. So it starts with 0, 0, 0, 0 up to nt, and then I keep this. And this one stops with 0, 0, 0. So I can assume it's in this space that has fixed dimension. My weighted L1 norms are increasing with the dimension. So these have all norms less than 1. So I'm in a bounded set in a finite dimensional vector space. So I can extract a converging sequence. So up to throwing things away, I assume that my sequence here, the minus part converges. Okay, now I go to the functions I associated, and I split them the same way. The first nt, the last nt. And what I have, this thing, my hypothesis, that they go to 0 in L1. This one converges, that's equivalence of norm. This sequence converges, so it's Cauchy. So well, the sequence of coefficients converges. It's Cauchy. You control the phi n minus phi n minus by the coefficients. So this one is Cauchy, so it converges. And this converges, so this one converges to 0, so this one converges to minus this. And now what I use, but for this one I have Nazarov's inequality, so it tells me that the Cn plus converges also. It's always the same argument. You go through Cauchy, and then it's Cauchy, so it converges. Okay, so the Cn plus converges, the Cn minus converges, so the Cn converges, and I can just say it's like a sequence C minus C plus in this. So it converges, but in this space, which is not a very good space. Already L1 is not so good, but this one is weighted L1. And because each of the Cn here has norm 1, the ultimate vector has norm 1 as well. So I will have a contradiction if I show that actually all coefficients here are 0. And this, I have some trouble doing it directly. So what I will do is I will just integrate these functions. So you see, not to have a problem, I have to remove the 0 frequencies, but that's nothing. I just translate everybody a little bit. Okay, so if I integrate, I get this, and you see that the integral of a trigonometric sum is again a trigonometric sum. Polynomial, I should say, provided you don't have the 0 frequencies, otherwise you would have a t. It's not a big deal, but it's just annoying. So little phi's go converge in L1, so the capital phi's converge uniformly, in particular they converge in L2. Okay? But so this guy will go to somebody, that is this. So in my A case or the C case, and this convergence is again uniform, so in L2. Okay, and now what do I do? Well, the sum goes to 0. It's also true for the minus, because one goes to plus, see the phi minus goes to integral of phi minus, and the phi plus goes to integral of phi plus, which is minus phi plus, phi minus. So the sum goes to 0. So the L2 norm is 0. But the L2 norm, I can this thing I can write. It's just this. And now I'm exactly, to see this convergence, I use that the gaps go to infinity and dominated conversion. And now I'm exactly in our current situation, because the gaps go to infinity. So even with t is very small, I get more than this constant. But it is 0 is more than this positive thing. So each of the terms here is 0. All the CKs are 0. So I get the conclusion. So the problem is, you saw that this is a proof by contradiction and compactness argument, so it cannot be quantitative. And we would really like to have something quantitative. So if you have a better idea, we would be very happy. So I think that's all. Yeah, it's all for today. Thank you for your attention. If you have questions.
Thank you, Philippe. I didn't need to interrupt you. You are exactly on time. Thank you for this talk. Are there any questions, please? Are there any questions, please?
I have a question. So thank you, Philippe, for this nice presentation. What if the gap, I mean, depends on n, the number of sequence tends to 0 when n goes to infinity, something like that.
Dr. Wissam?
Yes, okay.
You listen.
Yeah, try
Tell
to.
me, Dr. Wissam.
Yes, yes, please. There is a question right now, and I will be back to you.
Okay, so where is it? It must be somewhere. So you have, the thing is, what you want, that's the thing that's really important. You want here a constant that does not depend on n. Otherwise, for fixed n, because you want then to have this n going to infinity. That you can only do if the constant here goes to infinite, depends on n, you cannot make limiting arguments. So what is happening is that if this gaps here, so you don't see the gap if you fix the n. Okay, you only see the gap if you let the n be arbitrarily large. In this case, the gap will play a role. And what you can do then, if the gaps go to infinity, you can have this t arbitrarily small. Otherwise, this t has to be larger than 1. See?
Yeah, but 1 is related to the gap 1 somehow.
Yeah, 1 is related to the gap 1. So, okay, maybe this I didn't explain properly. Do I get the tools? I do this. Non. J'ai perdu le partage, non, c'est ça?
No, I can see your slides.
Ah, okay, but I lost this. I lost the slides. Okay, je vais enlever ça. Okay, sorry, I lost the slides. I apparently doesn't work. If I put here a gap that is gamma, this one I replace by gamma, then this one becomes 1 over gamma. That's just direct scaling. You just, how do you do? If lambda j minus lambda k is bigger than gamma, then lambda j over gamma minus lambda k over gamma is bigger than 1. So you write this lambda j over gamma t gamma, and then you write s equals t gamma. And you see that this t becomes t over gamma. Okay, so you need t over gamma to be larger than 1. No, it becomes t gamma, sorry. So you need t gamma to be larger than 1. So it's t larger than 1 over gamma. If you have gaps that are 1 over 10, then you need t to be larger than 10. Okay. Now, the thing that you can have the feeling of is that, and this is actually what the proof tells you, is that if the gaps become larger and larger, then the first ones are not so important. It's really what happens at the end. But this argument is a bit dangerous because you see in Gam's counterexample, there is just one gap that is not 1. Actually, that's the strange thing. All gaps are 1 except the first one. So you have a gap that is too small at the beginning, and that breaks the whole thing. So it's not just see, we really use that it goes to infinity. We did not just use that the gaps become large enough. Okay, so this is what I think. I hope I answered your question.
Okay, thank you.
There is another question from Fatih Bouzafour, I think.
Thank you very much, Doctor. You listen to me, Wissam?
Yeah, we can hear you.
Yes. There are similar to exponential Fourier series. There are Ramanujan series. Fourier series, Ramanujan Fourier series. So, or Ramanujan sum. The Ramanujan sum, if we take primitive root of unity and we sum over the k which are prime with n. So if we take epsilon, root of unity, primitive root, and we take the summation over k is relatively prime with n. So this is Ramanujan sum, and the Ramanujan sum is fit naturally with the number theory. For example, the extreme case C, if we denote Cn, the Ramanujan sum, Cn is the Mobius function, and Cnn is the Euler function. So we can also, the Ramanujan sum also have some orthogonality relation, like Fourier series. So my question, if we can try to work with this sum instead of exponential function.
So there is one difficulty, maybe something like Ingham. What is the proof? Ingham's proof can be a little bit flexible. This I'm not, because you see the proof is just this trick. The first trick is not that much. The second trick, well, first is not much. The second is not much. See, it's just you have a something partial, you get to a full thing. The third trick is still not much, and then it's Fourier inversion. So the difficulty is to have the right conditions. So something like this may be valid for other kind of summations for which you have pass one. Nevertheless, here you use a strong property of the exponentials, which is this. So that I'm not that sure that this would fit in your picture. The L1 case uses really extremely strongly the exponential, that they are exponentials. There are things like dyadic decomposition of the frequencies hidden behind, and properties like this. And I'm not convinced at all that it is very amenable to other types of Fourier series. So there I have more doubts. I think there's also, but maybe that's hidden behind. There's a paper by Green and Rouja in the discrete setting. I think it's called Little Root Problems in the Primes or something like this. So maybe they would be more experts to answer your questions. So I personally don't really, I have never worked with this Ramanujan sum, so I cannot answer like right now in whether there's a chance or not that you can do something. And if there should be, I would start with the real case. See, even something like this, if instead of having exponentials, you would like to go to higher dimensions and do something with spherical harmonics, well, the first lines are possible, but once you're here, you have g hat of t and a product of spherical harmonics or something like this, and you cannot do much. Orthogonal polynomials, it doesn't work, things like this. So, that I cannot answer if there's a real chance to say something or not. I'll let you try.
Thank you.
Other questions, please? Okay, then in this case, we would like to thank you so much, Philippe, for this nice talk. And please don't forget to send me your slides. And see you hopefully in the next session of video. Okay. Thank you.